Magnesium stannate graphene supercapacitors, upgraded with tartaric acid. Synthesis and characterization by Manuel Alejandro Navortis. Abstract. The fabrication and electromechanical characterization of magnesium stannate graphene supercapacitor. An electrolyte tartaric acid. The conductive electrodes of this supercapacitor were magnesium stannate graphene and the tartaric acid electrolyte, respectively. According to electromechanical tests, the maximum capacitance and specific energy were 617.8 farad per gram and 134.2 watts-hour per kilogram. The magnesium stannate was synthesized by solvothermal magnesium chloride and thin chloride. Furthermore, we use the tartaric acid. This with the purpose of analyzing its possible use in the development and construction of supercapacitor. The characterization of a magnesium stannate supercapacitor was carried out using the XRD, SEM, and UV-Vis techniques were performed for each to prepare materials. The magnesium stannate showed a low dielectric loss. The results on this work demonstrate that the tartaric acid and the magnesium stannate option for electrolyte and electrode to improve the stored charge. A supercapacitor, also called ultracapacitor, is a high-capacity capacitor with a capacitance value much higher than the other capacitors, but with lower voltage limits that bridge the gap between electrolyte capacitors and rechargeable batteries. It typically stores 10 to 100 times more energy per unit volume or mass than electrolytic capacitors, can accept and deliver charge much faster than batteries, and tolerate many more change and discharge cycles than rechargeable batteries. A typical supercapacitor comprises dual electrodes separated via a porous separator in an electrolyte medium. When the voltage is supplied, accumulation of opposite charge at the two electrodes will result, and this charge will generate an electric field that will allow the supercapacitor to store energy. Generally, on the basis of the energy storage mechanisms, supercapacitor can be classified into two categories. One is the electrical double-layer capacitor, where the capacitance comes from the pure electrostatic charge accumulated at the electrode or electrolyte interface. Therefore, it is strongly dependent on the surface area of the electrode material that is accessible to the electrolyte ions. First, a solution of magnesium chloride is mixed with a solution of thin chloride. After mixing, then sodium hydroxide is added until a pH of 10 is obtained and the precipitate is observed. When the precipitate is obtained, it is placed in a reactor and heated to 200 centigrade for 24 hours, then filtered with a vacuum pump and finished drying. Results. First, we have the XRD that indicates the diffractogram obtained from the magnesium stannate sample. The intensities are taken as peak heights, which can analyze and compare to say if that we are really analyzing is magnesium stannate. Then we have the UV visible spectrophotometry. It's a quantitative technique used to measure how much two chemical substances absorb light. Absorbent spectra of the magnesium stannate nanoparticles were recorded utilizing the Perk-Elmer lambda 900 UV near spectrophotometer in the range of 200 to 800 nanometers. Then we can use the dot plot with this graphic to know what is the band gap in the semiconductor. We do the calculate and we obtain that the band gap is 2.66 electron volts. Raman spectroscopy is a spectroscopy technique typically used to determine vibrational models of the molecules. And the Raman is commonly used in the chemistry to provide the structure fingerprint by the which molecule can be identified. As we can see, there is only one important peak before 200 Raman shifts. Now we can see in the SEM micrography, we can observe that magnesium SN8 has a uniform spherical morphology. It has a homogeneous size, distribution, and morphology. Now we go to the results in the electrochemical characterization. First, we see the cyclic voltamperometry of magnesium SN8. The voltamperometry is an electrochemistry technique that applies an electrical potential to an electrode in a dissolution with an electroactive species electrolyte. This technique is used to measure intensity of the current in the magnesium SN8 electrode. As we can see, the area is semi-rectangular, which tells us that the current increased exponentially at the beginning of the test, which is good signs we will have more current, which is what we are looking for. In the chronopotentiometry, we can observe that the highest peak can reach up to 13 volts and that no matter how many cycles pass, the material does not degrade and maintains the same properties through the cycles. Conclusions. The SN8 is very stable material that we can see in the chronopotentiometry because they are not changed along the cycles. The area of the cyclic voltamperometry are semi-rectangular. Area that magnesium SN8 with graphene represent a capacitor response like the one reported in the literature. The tartaric acid is an excellent electrolyte which can be substituted for most of the electrolytes currently used since it has a low price. The supercapacitor has a great results and they can be really useful.